Hi there and welcome back to the video lectures on the calculus of variations and introduction. You'll notice I've already drawn this out for us because it's a bit awkward to draw and I'm going to spend 5 minutes trying to get it all right. Now let me just explain what this is, and I hope it doesn't look too confusing. Let's imagine again we've got our piece of rope hanging from a couple of pulleys. Now here's a segment of the rope here, it's in yellow. Okay, that's a segment of the rope there sitting in its equilibrium position. Now if we were to linearize that segment of rope, we could draw a line from here down to the center point here, x2, and also a line from here to that center to that point, x3. Now if we were then to go and move that section of rope, so we put our thumb there and we pull the rope down till it hits this point, then the rope would have a different shape. I'm not going to draw it in because it just confuses the drawing. So it would have a different shape. It would come down something like this and round and down here. But what I've done is I've taken that new path and I've linearized that new path there. So there's a line going from here to here and a line going from here to here. Now we are interested in the change in the gradient that occurs whenever you move from this point to this point. Now quickly looking at this, it's quite easy to see that on this side, the left hand side of x2, the gradient goes from here, the blue line, to here, the pink line. So you can see that the gradient increases from the change that we've made from moving this point here to this point here. And on the right hand side you can see that that's the original gradient and that's the new gradient. So you can see that the gradient on this side has decreased. So now what we want to do is we want to write out a mathematical equation that defines the change in these gradients. Now what we could do, we could look at the original gradients. So let's look at this gradient here, from here to here. Now that gradient there, we could call that, we call it y derivative of x. Okay, and the gradient there is really defined at the point x1, and that will equal, if we call that distance there delta y1, and that distance there is delta x, then the gradient would be delta y1 upon delta x. So that's the first one. Now the second one, if we look at the gradient from here to here, the second one, the gradient would be y derivative of x, and that would be defined at the point x2, that's going to equal delta y2, which is, if I don't want to draw out too many more lines in it, but if you come across here to that point there, it's going to be that height there. And that height there is the rise of this line here. So it's the rise, we'll call that delta y2. And again, the run of it is from here to here, which again is delta x. Delta x. So that's us got two of them. Now I think I'll change colour so that we know that this is referring to the new gradients. So we'll go on to number 3. Number 3. Now in this one we're looking at the new gradient. The new gradient, we'll just call it y derivative at x defined from x1 is going to equal, well, it's the delta y, okay, which gives us our original position, and we're adding on the change, the perturbation of the change from shifting this point here to this point here. Now we'll call that small change another delta y, but we'll use small delta. I believe that's a small delta. Yeah, I believe it is. And the run for this one here is again delta x. Delta x. And lastly, number 4, we have y derivative of x defined from x2 is going to equal, well, this time we're looking for this one here, so we're going to have our delta y2, which was this one here. I'll just put delta y2 so we remember it. Delta y2, which was this height here, right? Delta y2. But now you notice that it's not that full height anymore. That comes along here, it's not that height anymore. It's only that small height here. Okay, so it's only the small section, because you can see that this gradient here has become shallower. So delta x has remained the same. So that delta y2 must be smaller, and it's smaller by a factor. That's a factor there, it's smaller by delta y. Okay, just sit and have a wee look at that, convince yourself of that. Okay, so that's minus delta y upon delta x. Okay, now I'll go back and I'll just go back to my usual colour. Let's see what this is. Now, what we are interested in is the difference between these, because that's what we're looking for. It's the change that has occurred. So that's the original, and that's the new one. That's the original, and that's the new one. So we're going to take one away from the other. Okay, so what we will have, if we take this away from this, so we'll say, let's just write it in long term, we're going to have 3 minus 1 is going to equal, well, is that a common denominator there? So it's going to be, that's a 1 there as well, I missed that out. So it's going to be delta y1 minus delta y plus that large delta y upon delta x. So basically that one there is going to cancel out with that one there. So you're going to end up with delta y upon, well, redo that, upon delta x. And in the same vein, if we do 4 minus 2, 4 minus 2, we're going to give us this minus that. So again, that's going to cancel with that, and we're going to end up with minus delta y upon delta x. Okay, so now if we were to then look at the change in S2, we'll call it the change in the value S, and we'll call this change 2, because remember the first change we were looking at was a change in position. Now this is a change in gradient. So the change in gradient, as per what we were looking at previously on the last video, would be df by d. Now it's dy derivative, because we're looking at the change in the function. The previous one we're looking at the change in the function due to its change in position. Now we're looking at the change in the function due to the change in the rate of change of position. So that's df by dy derivative at x1. Okay, that's the x is the is kept constant, and if we multiply it by the change, now the change we're going to have is delta y derivative of x, and we add on again df by dy derivative at x2 times delta y derivative of x. Obviously that's at x2. So don't get confused with this. We're just doing the same thing here as we had done previously with the position change. The only difference now is we're looking at the change in the function not with respect to the change in position, but we're looking at the change in the function with respect to the rate of change of the position, which is the gradient. So whenever we're multiplying it by a small factor, we're multiplying it by a small factor not of y of x, which is the position change, we're multiplying it by a small factor of the y derivative of x, which is the rate of change of position. Okay, so if you're unsure about that, go back to the previous video, and I think that will become more clear. Now, if we then place these in for here, we will get delta S2 equals df by dy derivative by x1 times delta y derivative. Well, the delta y derivative we just worked out is that dy by dx. In this case here, the delta y derivative is minus dy by dx, so we'll put in the minus here, minus df by dy derivative at x2, and that's dy by dx. We'll bring terms together, we could look at that, and if we make that look at minus, then there's a reason for writing it in this form, and you'll see in a minute. df dy derivative at x2, which is this one here, minus, because the two minuses will have to make a plus for this thing here, df by dy derivative at x1, and we take out the common factor of, let me do that again, take out the common factor of delta y upon now, delta x. I should actually have written that as delta x because it's just a small change, it's not a, it's that delta x here, and I think I'll have done the same, I've done the same throughout there, so these should be delta x's here, delta x, and it should be that delta x there as well. Okay, so that's fine. Okay, now the reason for writing it in this format, taking the minus sign out and then I've been left with this and this, is that if you look at this term here, it looks very like the definition of a derivative. Now the definition of derivative would be limit as, let's see, delta x tends to 0 of f of x plus delta x minus f of x all upon delta x. Now if you look at this one up here, we could take this delta x down here, okay, and then we would have df, we have df by dy derivative minus df by dy derivative at x1. But you noticed that up in here, x2 equals x1 plus delta x. You see, x2 is the x1 plus a delta x. So when we come down here, we can write that as this one here. I think I'll get rid of this so as it doesn't get in the, no, I'll just leave it there just now because you know that's not part of the line of thought, that's just an aside. Okay, so if you look at this here, we can look at that and we could write that there as, and I'll write it actually out in long term, longhand, we could look at that as the limit as delta x tends to 0, and we could write that as df of, now there would have been an x there but it's understood that x, so we're not going to write it down every time, but you could do it like that. The limit is f10, the limit is delta x tends to 0 of df of, now that would be x plus delta x, because that's what x2 is. x2 is x plus delta x, or x1 plus delta x I should say. Okay, by dy derivative minus this term here, which is df of x1 upon dy derivative all upon, oh, see if I can get a line here, all upon delta x. Now this here is just like a derivative. Okay, So that there can be written out quite simply as d by dx of df by dy derivative, okay, all times their value delta x. Let's see, delta x. Yep. So then we can now, we're near the end, okay, so almost there. So we can write delta S2 equals, and of course let's have a look and see, there's actually, there's a minus sign there as well, we missed out. So there's that section there, but there's a minus sign there as well, and that should be, let's see, delta y. Yeah, so that's incorrect there. That should be delta y. Let's have a find my rubber. Oh, let's not do that. That's not what we want to do. Yeah, I think I can undo. Oh, there we go. It's all back. That's good. That was nearly a disaster there. Let's see, is that the rubber there? That's my rubber there. Okay, so go back to my pen. That should be delta y. Delta y. And that's the minus sign here. Right, so that's a minus sign for here. That's the delta x coming down here. And x2 equals x1 plus delta x gives us this here, and that can be written as d by dx, df by dy derivative. That there, we've got a minus sign, and we've got our delta y left over here as well. Okay, so that's all fair and good. So now we can write, if we have, now that there, well, I'll just write that actually, so it's minus d by dx df by dy derivative times delta y. Now that there is our delta S2. Now we're now at the point where we were in the previous video. That there is the change in the value of S due to the change in the gradient. Now we'll continue with this and we'll finish off and get the final equation that we're looking for, because all we need to do is add the two together. So what we'll do is we'll add delta S1 plus delta S2. That equals, if remembering back, is df by dy times delta y. Whoa, that's not quite right. No, that's partial. Get the rubber again. That's the rubber. Right, just to get it right. Okay. So that's partial f, partial y by dy. Okay, and we're adding this term on, so that would be minus d by dx partial f by partial y derivative times delta y. And now, I hope I've got enough space at the bottom here. That's going to equal, take out the common factor of delta y df by dy partial f by partial y minus d by dx of partial f by partial y derivative. Okay, so that's us got that there. But now, all the way along we've been saying as delta y would tend towards 0, it will be very, very small. Then what we will have to do is, in order for us to in effect return the rope back to its equilibrium point, we'll have to make all of that 0. So we'll have to say all of that must equal 0. Okay, now delta y is a small value, so it's not equal to 0, but it is a small value. So what we have to do is make this term here equal to 0. So now we want, and I'll write it bigger here, we want df by partial f by partial y minus d by dx of partial f upon partial y derivative. We want all of that to equal 0. Now this here is the equation that we've been trying to work out over the last 2 videos, and this here is called the Euler Lagrange equation, after Leonhard Euler and Mr. Lagrange. I don't know his first name. So this here, it gives us an indication now, because of the way we've derived this, we're able to look and see what these terms mean. And remember, this equation is an equation which defines all the changes that occur due to moving the rope from one position to another. So in this term here, that is a change in the function with respect to y that occurs just by changing the position, the y position. And this here is the rate of change of the function with respect to the change in the gradient. And we noted that this rate of change of the function with respect to the gradient, there was 2 parts to it. On the left hand side it increased, and on the right hand side it decreased. So what we have to do is we have to take and look at the rate of change of the change of this gradient. Now these 2 things added together gives us the complete change in that system. And as I said, we will be able to find our values of y of x using this equation here, because we can work out a characteristic function, Now the characteristic function that we worked out for the rope, remember, was the y of x root of 1 plus y derivative of x squared by dx. So we can put this into here, make it equal 0, and then we're looking to find this function here. So once we put this in here and we churn it round to get a result, then we can transpose the result so that we find out what y of x is. Okay, that's all there is for that. It's quite a long-winded one, and it's quite some awkward maths, and I hope I've got it right. If I've got any wee bits wrong, you can always put a little comment in. Okay, now that's enough for the maths there. What we'll do next is look at solving this here using this, and then after that there'll be a few other videos on a more analytic method of deriving this, which was thought up by Lagrange. This method here is a method that was used by Euler, and it's quite an intuitive method. So that's all for this video. Thanks for listening, and I'll get you in the next video. Goodbye.